Now we're going to look into the example 1 on solution part B, where we are actually dealing with the closed system. Okay, so for the closed system, when we write the equation again, it started with delta U plus delta EK plus delta EP equals to Q minus W, right? So is there any kinetic energy involved? No. So is there any change of potential energy? No. Is there anything work done from this? No. It's just a heating of the saturated steam to become superheated steam. So there is no work done by the system. So it's 0. So what happened now is only delta Q, delta U is equals to Q. Okay, so Q is the amount of heat that will be able to heat up the steam, the saturated steam, to become a superheated steam. Right. So whenever that we put in the equation, right? So delta U, in order to calculate delta U, is simply like M is equals to U specific internal energy outlet minus specific internal energy inlet. Right. So you were given the M is 100 kilogram. And with using the same ways of looking at the appendix in the table, from table B5 and from table B7, you'll be able to get the value of this for the specific internal energy. Right? So when you substitute in here, then you'll be able to get this number. So what does this number means? It means the amount of heat that is required actually to change the internal energy from the initial to the final. So I would supposed to be named here, this is supposed to be final and this is supposed to be initial. Okay. Let's have a look at another example where we are talking about saturated steam at 1 atmosphere is discharged from a turbine at a rate of 1150 kg per hour. Superheated steam at 300 degrees Celsius and 1 atm is needed as a feed to the heat exchanger. So you see the keyword here is that there is a turbine and there's also heat exchanger, right? So there are two equipment here, 2 unit operation here. To produce it, the turbine discharge stream, okay, is mixed with superheated steam available from a second source at 400 degrees Celsius and 1 atm. Okay, so you have a second source at 400 degrees Celsius and 1 atmospheric pressure. So the mixing unit operates adiabatically, and then they calculate the amount of superheated steam at 300 degrees Celsius produced and the required volumetric flow rate of the 400 degrees Celsius steam. Means that you have to calculate the amount, what would be the steam at 300 degrees produced and the required volumetric flow rate of the 400 degrees Celsius steam. So from here you can see that the term adiabatically is being introduced here. What does it mean by adiabatic? Okay, adiabatic means that you are not using any external heat. There is no heat being released to the surrounding, or there is no heat taken out from the surrounding to the system. It's entirely using the stream itself as the heater or as the cooler. Okay, whatever stream that is coming in, it becomes the heater, or whatever stream that is you want to and then whatever stream that is coming in as well, that is also become a cooler towards the system. There is no additional, for example, you give external heating, for example, nothing like that. Okay, so that is what is meant by adiabatic. So when we look at this problem, first of all, you have to remember that we need to draw the flow chart. Okay, so how does the flow chart would look like? This is the flow chart. How would it look like? Because initially you have a turbine discharge, okay, saturated steam at 1 atmosphere, and then you have the flow rate, which is 1150 kg per hour. We didn't know what is the temperature for this stream, okay, but we also have been given superheated steam at 400 degrees Celsius and 1 atm, and we didn't know what would be the flow rate for the superheated steam. Okay, so the combination of this, okay, the combination of this flow will adiabatically gives the temperature at 300 degrees Celsius, which means that there is no heater provided. Okay, there is no heater provided here, so there is no heater here. to the mixer. So this particular steam will be used into the heat exchanger. Here we are not that interested in the heat exchanger. Okay, the heat exchanger just will receive the final superheated steam at 300 degrees Celsius, and what we are interested at is actually at this border. Okay, so how do we do this? Remember, after we do the flow sheet, flow diagram, we draw the flow chart. The next thing is actually we try to solve the material balance before we proceed with the energy balance. Okay. However, you can also look at some kind of information. Okay, you can look at some kind of information from the system. Okay, from the system here, you can look from the information, such as you will be able to get if you go to table B6 and B7, then you'll be able to get the specific it's supposed to be properties of, okay, specific enthalpy and specific volume that you can get from there, which is saturated steam at 1 atmosphere. Okay, this is in flow, this is in stream 1, we call it stream 1, stream 2 and stream 3. So saturated steam at 1 atmosphere is given as per stream 1, this is stream 2 and this is stream 3. Okay, so if you look for the details, saturated steam at 1 atm, if you go to table B6, so let's have a look at the table that we want to use. Let's have a look at the table that we are given, which is we start with the table B5 because we're talking about steam. So when we look at the information here, right, so what we need to know is actually the saturated steam at 1 atmosphere. So how do we get this? Then we go at 1 atmosphere. We don't look here because this is based on the temperature. So if we want to look based on the pressure, so we go to table B6. So table B6, we go straight to 1 atm. So 1 atm is somewhere around here. Okay, so 1 atm, the temperature is given as 100, right? And then we were given the volume, internal energy, as well as the specific volume, specific internal energy and specific enthalpy. In this case, we are dealing with steam, we're not dealing with water. So when we go to steam at 100, okay, so we got the volumetric specific volume is 1.673 meter cube per kilogram. Okay, and then when we look for the value for specific enthalpy of steam at 100 is at 1 atm is 2676. Okay, so we can write it down here first. The second one, we're looking at superheated steam at 400 degree and 1 atm. Remember, at 400 degrees Celsius, this is actually superheated. Then we go straight to table B7. So in table B7, again, we go to 400 degrees Celsius at 1 atmosphere. So here, this is 400 degree. So we got 3278 as the specific enthalpy, and the specific volume is 3.11. What else? Superheated steam at 300 degrees Celsius. Again, this is actually can be obtained from superheated steam table, which is at table B7. So when we go to table B7, we look at 300 degrees Celsius, which is up here, right? And the pressure is 1 bar. Then you got 3074, and the specific volume is 2.64.